we were looking at finite field extensions. So let K over F be a extension field extension. Means K is a field that contains a field F. Whenever you have this situation, one field contained in another field, I'll often picture it like this. The bigger field becomes a vector space over the smaller field. So it has a dimension, maybe infinite, but has a dimension. This dimension of K as a F vector space is called the degree of the extension. And we say that this extension is finite if this degree is finite. So these are the kind of extensions we are looking at. Example being, you take polynomial ring in one variable over a field F and quotient out by a irreducible polynomial. Then you'll get a field K, and this is an extension of F after you have identified F inside K in a natural way. And in fact, if F, this polynomial little f, has degree n, then this is exactly an extension of degree n, because this K is actually isomorphic as a vector space to polynomials of degree less than n. We can express every element here uniquely by coset of a polynomial of degree less than n. You give me a polynomial of degree less than n, I take its coset. And this is actually a vector space isomorphism. And this is clearly a n-dimensional F vector space with basis 1 x squared through to x to the n minus 1. So this one also is. Okay? So these are the kind of extensions we are looking at. And we look at this because in this extension, f has a root, whereas because little f was irreducible in capital Fx, it didn't have a root in capital F. But in capital K, the polynomial has a root. Okay, we have this theorem, sort of the all-important theorem that we'll use over and over, that when you have a tower of extensions, meaning three fields F, which is contained in a bigger field K, which is contained in a bigger field M. Such a situation is called a tower of extension. Then the degree of the big extension is the product of the degrees of the two smaller extensions. In fact, the big extension is finite if and only if the two smaller extensions are finite. And when things are finite, you can make a more precise statement. If A1, A2, Am is a basis for K over F, and B1, B2, Bn is a basis of M over K, then if you take their pairwise product, that will be a basis for M over F. That's the statement. So that implies immediately that the degree of the big extension is the product of the two smaller extensions, because if this is M and this is N, then this is Mn. Okay, so let's check that these pairwise products span the big vector space over the smaller field. So take some V in M. You can write V as a combination of B's, as a linear combination of the B's with coefficients coming from K. That's what it means to say that B1, B2, etc. is a basis of M as a K vector space. For some see, all these sums are finite, by the way. There is only n terms in this sum, but I'm just going to write dot dot. Now, this K's, this K1, K2, etc. can also be written in terms of the A's with coefficient in F. So K1 is an element of K, which can be written as a linear combination of A1, A2, etc. with coefficients in F. Let's call them F11, F12, etc. And then K2 can be written in the similar way. I'm just choosing double index so that these little Fij's are all different. This is also a linear combination of A1, A2, etc. So this is maybe F21, A1 plus F22, A2 plus etc. Dot, dot, dot for each of the n things that you have. This goes up to K n Bn, right? Now all I need to do, I need to write V as a combination of the Ai Bj's. So I take this equation, this expression for V, and I substitute the expressions for the K1, K2, etc. So this will be F11 A1 plus F12 A2 plus dot 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 times V1 plus F21 A1 plus F22 A2 dot 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 V2 plus dot dot dot, which if you expand is F11 A1 B1. All these multiplications are now happening in the big field M. Everything that you see in this right hand side, this lives in F, these live in K, these live in M. But F is a subset of K, K is a subset of M, so everything lives in M, and M is a field. So all these multiplications, additions, you can think of happening in the big field. Plus F12 A2 B1 plus dot 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 plus F21 A1 B2 plus F22 A2 B2 plus dot 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 plus dot dot dot. And what have you done? You have written V as a linear combination of exactly these guys with coefficients in F. So these AIBJs AIBJs how many there are? The i's go up to M and the j's go up to N. Form a basis. Oh, I've only shown that they span. M as a F vector space. Maybe that's all we'll write. Let's see why they're linearly independent. I also want to check that these vectors, these elements of M that I'm overbracing right now, are all linearly independent over F, right? I want to show that they form a basis. So they have to be linearly independent over F. How do you show a bunch of vectors are linearly independent over F? Suppose some F linear combination of these guys is equal to 0. So suppose such an expression is equal to 0. And then you have to show that all these coefficients are 0. All these coefficients. Right. But this expression, this big expression, I mean this one, is same as that expression. So because this expression is 0, you get that this sum is also 0. Okay, but what does that tell you? The upper expression is now a linear combination of the b's with some coefficients in K. And because the b's are linearly independent, the b's are after all a basis, you get that each of these expressions are 0. And now you take that this is equal to 0. This is now a linear combination of the a's with coefficient in f. But the a's are also linearly independent. That tells you that f's are 0. And then similarly, this one is 0, tells you these f's are 0, and so on and so forth. So you just go in 2 steps like that. And that's basically the proof of this theorem. So the next thing I want to do is introduce algebraic extensions. Now this point, the theory sort of jumps very quickly. Even in like 1 or 2 pages, it gets fairly serious, so please pay close attention. An element, so still let K over F be an extension field. An element of the big field is called algebraic over the small field if there exists a non-constant polynomial, a non-zero polynomial, such that P of A is 0. So A satisfies some polynomial equation with coefficients in F. And we say an extension is algebraic if every element in the big field is algebraic over the smaller field. We say K over F is algebraic if every element of K is algebraic over F. So example, like root 2 in R is algebraic over Q because this number satisfies a polynomial equation. So this is a polynomial in coefficients in the small field, and P of root 2 is 0. So it's a root of an algebraic equation, so it's called an algebraic number. Similarly, this is called an algebraic element over F. Okay. Whereas pi is not algebraic, right? Those are called transcendental numbers. I mean, this is hard. This is a non-trivial theorem. You know this is true, that pi does not satisfy any polynomial equation with rational coefficients. Yeah. So when you're trying to solve polynomial equations, you're really trying to understand these algebraic numbers. And the number theorists are really interested in these algebraic numbers and so on. So that's one place where field theory and abstract algebra actually started. Well, what relates these algebraic extensions with finite extensions is this theorem that if a finite extension is necessarily algebraic, a finite extension is algebraic. And this is surprisingly straightforward. Let K over F be a finite extension. You take A in K. Then K is a finite dimensional vector space over F, so 1A, A square, A cube, etc. cannot all be linearly independent over F. So sum F0 plus F1A plus F2 A square plus AN F to the n is 0. Sorry, Fn A to the n. For some F1, F2, Fn in F. And there is a polynomial with F coefficients that your A satisfies.